Hello YouTube, how are you? I'm very excited today because finally we will be talking about the Heisenberg's uncertainty principle, which is one of the most profound theories in quantum mechanics. So Heisenberg's uncertainty principle has also proven its importance outside of the quantum realm, but today we will be talking about three different ways we can visualize the Heisenberg's uncertainty principle. So first, let's jump back to 1801 when Young did his single slit experiment, where he passed an electron or particle through a very narrow slit, and he observed some really interesting results at the screen behind that. So let's get to it first.
So we are talking about the experiment that Thomas Young did in the early 19th century. So through this electron gun, I will be releasing one electron at a time, such that not two electrons will ever have contact with each other. And I will be observing where the electron lands in this screen as it passes through this very narrow slit. Now, this slit doesn't look very narrow, but it's actually very narrow. But I've made it look less narrow because of an ease in intuition for you guys. So, let's release our first electron and let's see where it lands. And even I don't know where that electron will land. Okay, so this electron landed here. The second electron landed here. Third electron here. Fourth electron here. Let's now release many electrons at a time and let's see where they land. So you see, I can actually judge or I can actually assert the position of the electrons on this screen by the means of probability. I can say that the most electrons land here. So let's release many electrons and let's see where most electrons land. Okay, that's perfect. So this is the region where the most electrons land, which is the point at the slit hole. And some electrons land away from it. So this is what happens when you have a slit which is a little bit narrow, but not too much narrow. I will get into the details later. But now, let's try to change the distance of the slit and let's see what happens to the electrons. Okay, so now as you see, the distance of the slit or the value of d has decreased tremendously. But now, let's see where the electrons land. Now I will release my first electron again. But now, since I have decreased the value of the slit, the electrons will get more momentum for the reasons that I will explain later. So this electron has landed here, this electron here. Remember, now this electron has gained more momentum and that's why it has landed further away in the screen. This electron here. So as you can see, the electrons are getting more momentum in the y direction such that they are getting more spread out, just like a wave. Let's release more electrons now and see what happens. Remember, any two electrons are not in contact with each other such that to affect their motions. So, electrons are landing and are getting more spread out to get a more spreading out interference pattern. So let's release more electrons. Okay, so as you can see, I'm getting an interference pattern here, such that still most electrons are landing in this part, but now the electrons are getting more spread out, and such that I can say that the electrons are getting more momentum in the y direction as I decrease the value of the slit. As I decrease the value of d, the electrons are getting more p. And that is the thing that you can get from this animation. As I decrease the value of the distance between the slits, the electrons are getting more spreading out, and the electrons are getting more momentum in the y direction, which is literally what the Heisenberg's uncertainty principle says.
So let's do on the board what Young did, and let's create a gun that ejects electrons. So this is, well, excuse my horrible drawing again, but this is an electron gun, and let's also draw some slit. And we can always control the distance d between the two slits. So, shorter distance, and let's also make sure that there is a screen behind which detects electrons that fall into it. So this will show me where the electron has landed. And if I eject in numerous number of electrons, billions of electrons, then what I'm gonna get is a constant pattern. The pattern is gonna be something like this. There are gonna be some electrons here, but the more electrons are gonna be dense, at the point where the slit hole is. And this is what Young observed. And that's why we can say that we have to rely on probability when we try to study quantum mechanics. Because when I release the first electron, when I press a button, and when I release the first electron of this ejector, I don't know where this electron is going to land. This electron can land maybe here, you know, this is also a probable region where the electron is present. This is also one of the region, this is also one of the region, I don't know. But after billions of electrons, I can say that the more electrons are present here. But back to Heisenberg's uncertainty principle. This is somewhere, so I can call that this d is actually delta x, which is my uncertainty in position, which is I can control for this experiment. So I can control the value of delta x, but as through the experiments, what I saw is that the electrons get some momentum. The electrons are straight here, but now they're getting a certain momentum in upwards or the downwards y direction, such that the electrons are getting more uncertain in its momentum. So I don't know what the momentum of electron is as I try to narrow the distance, or as I try to make sure that the distance is more certain. So by wave mechanics, I can say that the lambda, or the wavelength of these waves, is d sine theta. Or lambda equals to, since my d is delta x here, which is I can control, delta x sine theta. And also I know that E equals to hc by lambda, or equal to p times c. So let's see, c gets cancelled. So what I have is that lambda is equal to h over p. Two important conclusions here. But also try to understand this one. So as my momentum is p here, the momentum is not p anymore when I pass these electrons through the slits. If this is my p momentum, and then let's say this first electron, let's say it lands somewhere here. So this is where the electron lands. Then the change in momentum delta p is going to be equal to p times sine theta, trivially. So my p will be delta p over sine theta. But now let's say my lambda is h over p, and lambda is also delta x sine theta. Let's equate these two functions. So h over p equal to delta x times sine theta, or h equal to, h is a very small number, to having an order of 10 to the power negative 34. So h will be equal to delta x sine theta times p, which is delta p over sine theta. So delta p over sine of theta. Okay, perfect. So from this experiment, or from this calculation, what I get is a very important result. That is, I cannot actually measure the distance and the momentum of the particle at the same time. So delta x times delta p will be equal to h bar. Even more than the result of this calculation, you can get this intuition through this experiment itself. As I try to narrow down the distance of the electrons, as I try to narrow down the distance of these slits, the electrons are gonna get more spread out. The waves will also get more spread out, but the electrons are getting spread out, and that's actually a very important discovery, because electrons are particles, and this is where we got to know that the electrons also show wave-like nature. So similarly, according to the waves, as I try to narrow down the distance of the slits, the electrons, let's say if I narrow down the distance more, what I see is like a bigger pattern, like electrons are gonna get more spread out here. And it happens, like, because I'm confining the electrons at a certain, very certain distance. So I know the distance, I know the position of the electrons. But at this point then, I don't know what the momentum of the electron is gonna be. It can land more here or more here. And this is what basically Heisenberg uncertainty principle says. So this was our first way of trying to visualize Heisenberg's uncertainty principle. Now, let's try to see what happens when we try to take the wave function psi, or the quantum wave function, and apply wave mechanics, or Schrodinger's wave mechanics on it, to see how the Heisenberg's uncertainty principle plays out. So another interesting way of visualizing this thing is by the interpretation of the wave functions. So let's take a random wave function psi1. Let's take a wave, a plane wave, n, times e to the power I times kx minus omega t. And let's say this wave function is rotating around the x-axis or the position axis. So the normalized wave function should look something like this. And the probability from where I can get the position of this particle anywhere will be equal to psi times psi star, or n square times e to the power I km, okay, let's say e to the power I times 5 times e to the power negative I times 5, which get cancelled, and which will be just equal to n square. So the amplitude square gives probability of the function. And the amplitude here everywhere is just rotating. Here the amplitude is in pure complex form, that is rotated 90 degrees in the complex realm, and here it's pure real. But the amplitude is similar, and that's why I can find the probability anywhere in this region, not just here, but I can find it here, 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 and here. So I can find the probability. So the position of the particle is what I'm most uncertain about. So psi 1 for this certain wave function, this is not superpositioned, and that's why I can say that this wave function has an uncertain position. But as you can see, this function has a definite wavelength. And since you know that lambda is h bar over p, and I'm very confident about the wavelength of this wave function, and that's why I'm very confident about the momentum of this function. So momentum is certain, and position is uncertain for this particle. But now let's also take another example, which will be kind of like a delta Dirac function, superpositioning of many other particles, many other functions. So let's say I have a function which gives a peak at a certain position, which is, let's say, x naught. This is x, this is psi of x. So what can I say about this function now? Let's say this is psi 2 of x. So what can I say about this function? Well, in this function, I'm not confident about the wavelength of this function, but I'm confident about the position of this function because the amplitude of this function is rising or is peaking at this point. So I can say that the position of this particle is right here at x naught, but the momentum of the particle, not so certain, is it? So I can say position is certain, not momentum. So by these two types of wave functions, you can also say that by this wave function, if you are more confident about the wavelength of the wave function, then you are more confident about the position of the wave function, and that is why you are more unconfident or you are more uncertain about the position of the wave function, and you are more confident about the momentum. But for functions like these, you can say that you are more confident about the position of this wave function, but you are less confident about the momentum of this wave function because this wave function contains many other functions. And this psi is actually the superpositioning of many other functions. I will talk about superpositioning and Fourier transform in a different video. But for now, I hope you understand, just by interpreting different wave functions, how can you conclude the Heisenberg uncertainty principle? And how can you make sure that how the wavelength and the position cannot be certain, or the momentum and the position cannot be certain for certain wave functions. There are also middle conditions, but they are not important at this point, as these two conditions can be considered as an extreme conditions to find positions and wavelength or momentum. So now let's talk about a more profound way of interpreting the Heisenberg's uncertainty principle. This is by obtaining the expectation value of a certain quantum operator, in this case, the position and the momentum operator. So you might know about operators. They work on vectors to give a different scaled and rotated vector. Simply, a quantum operator works on the quantum wave function to give a different rotated and scaled functions. More about quantum operators in a different video. But for now, you need to remember about the position and the momentum operator. So operators are denoted with a cap, and the position operator, x cap, will work on a wave function psi. When I just write psi, remember it's psi x comma t, which is depending on position and time both. So psi x bar times psi will give us the position as its eigenvalue times that same function psi. This is the position operator. There's also a momentum operator, which is denoted by p cap times psi. And that gives us minus I h bar partial of psi with respect to position. Remember, it's not with respect to time. Momentum operator gives the partial of psi with respect to x. And the derivative is again very beautiful. But that let's do that on a different video. So these are the operators. Let's also write down some formulas for the expectation values. So expectation values can be about any operators. It need not have to be only position and the momentum. So for any operator, let's say O, the expectation value denoted like this will be equal to integral of negative infinity to infinity. This is also important. We are giving all the ranges since symmetry comes in, times psi star, complex conjugate of the function, times the operator working on psi dx. This is the expectation value. Expectation value. And now let's also talk about uncertainty. When you have the expectation value, you have the uncertainty. And this is equal to square root of the expectation value of O squared minus the expectation value of O squared, the whole function squared. So let's see what this is all about. So now I have the momentum operator, I have the position operator, I have the wave function, which can be any function you like. So let's try to calculate this. So my expectation value of the momentum, let's say, okay, let's do position first. So expectation value of the position will be, let's do it here. That will be more clear. So expectation value of the position will be, let's say, integral negative infinity to infinity psi star times, it gives x as its eigenvalue, so x times psi dx. This is the expectation value for the position operator. But to get the uncertainty in position, you also need the expectation value squared. So like expectation value squared will be in position squared, integral negative infinity to infinity psi star times x squared times psi dx. And these both values you need to remember if you want to get the uncertainty in position for any wave function psi. This is position expectation value. Now let's talk about momentum. Momentum expectation value is a little bit tricky, but not really. So let's say I have momentum operator. So my expectation value for the momentum will be integral of negative infinity to infinity psi star times minus I h bar partial of psi with respect to x dx. This is important. But now let's talk about the expectation value of momentum operator squared. So now I'm going to have to square this whole term to get the position operator of the momentum squared. So this will be negative infinity to infinity psi star times, so minus I times h bar. So I'm going to get h bar minus of h bar squared, because I squared is minus 1 and minus minus gets cut. So minus h squared. I hope I'm not writing slanting, because I observed in the last video I wrote everything like in a slanting manner, and that would be kind of annoying. So times minus of h bar h squared times partial squared, so dou square psi over dou x squared dx. So if you're writing down notes, please write down these formulas, because these formulas will help you a lot in calculating the expectation values and the uncertainties in momentum and position of any wave function of the quantum mechanics. So this is, let's say, no, this is actually momentum expectation values. This is the position and this is the momentum expectation values. So again, calculating these integrals are not easy. You need to define a very convenient psi, like a Gaussian distribution function. I'll give you an example like after a little bit time, but this is how you should calculate the expectation values, and after that it becomes very easy to calculate this term to get the uncertainty in position and the uncertainty in momentum. And then for any value psi, you can get the uncertainty of x and p with an order of h bar, which is the Planck's constant. So integral calculating this is not very easy. So I would recommend you, if you want to calculate the expectation values of psi, please pick up a psi which is actually a real function and which is actually not time dependent. That will ease you. That will actually prove very easy in calculating the momentum and calculating the position and momentum expectation values, and eventually evaluating these integrals. So let me give you a very small exercise before leaving. And that exercise will be, I will give you a psi, I will give you a wave function psi, and you have to calculate the expectation values. And I will also show you how to calculate the integral for that function psi. So let me give you a function to work with. So let's say your psi is e, let's also add a constant before, so n times e to the power negative ax squared. And that's it, that's your wave function. This is actually a Gaussian function whose amplitude depends on x, which can be plotted something like this. So you have your psi x and your x, and this function shows a peak at x equal to 0. So you know what your expectation value in position is. Expectation value is the average value where you get your position. And where your expectation value is at 0. So your average value to get the position, that is your expectation value of position, is 0. Although x squared is not 0. And I want you to calculate that yourself. Let me also give you a simple formula to calculate this integral. The general formula for the integration of the Gaussian, negative infinity to infinity, times e to the power, so this is your wave function, let me square that. This is your hint number 1, this is your hint number 2. So e to the power negative ax squared plus bx can be also written as square root of pi over a times e to the power b squared over 4a. Again, remember, there is no b part here, and that is why this thing will be 0, and so your integral will be pi over alpha. And this is a Gaussian function, so you can always plot this function to get the expectation values of the momentum and the position if you have MATLAB or any other mathematical software. So this is your function, and I want you to calculate an exercise for you guys to calculate the expectation values in position and momentum and the uncertainty, and then multiply those values and see if you get the Heisenberg's uncertainty principle proved. You get the h bar by the momentum operator, which works on this one to give you h bar or minus i h bar times dou times psi over dou times x. So this is your exercise. Please let me know in the comments if you get the answer, and also please let me know in the comments if you have any doubts while solving this question, and I will help you out. So that was it for the uncertainty principle. I don't think we have to explain any more for uncertainty principle. Those were the 3 levels of the uncertainty principle you have to understand. Third level is more profound, and you need to have some knowledge about integrals and complex functions to do that. But that was it for uncertainty principle. And if you have any doubts regarding this video, please let me know in the comments again, and I will answer you. Thank you very much for watching. Subscribe for more.